Hello everyone, my name is Samuel Dumbutz, and today I'll be talking about Lab 5, the world's largest rope swing. In this video, you'll see me observe and analyze the real-life YouTube video, create a computer model of the system, compare the model to the YouTube video, and describe the physics phenomena involved. This lab focused on the implementation of Newton's second law and the energy principle to predict motion with a non-constant net force, since both gravity and the rope, which I will be treating as a spring force, will be acting to create the net force. I will then create a glow script model to model the motion and predict maximum velocity and maximum spring force after modeling the real-life YouTube video. As I mentioned, we will be using the energy principle to ensure that the principle itself is satisfied throughout the entire time interval. As for our system, I used the mass of an average person according to Google of about 75 kilograms. The person will be hanging attached to a rope, which I determined to have a K constant of about 155. I empirically determined that by iterating the glow script model to match the real-life video in order to match the model that they show in the video. I also determined that it was 150 feet long because that is what they said in the video. Here is a little bit of the motion. You can see them swinging through here. I included the initial mass and the initial position here, which I converted to meters based on the feet measurements in the previous slide, and the initial velocity is 0 since they start at rest. And then I used a time interval of 0.008 because of the time range that I will show a little bit later. Here's where I input most of my constants: the G constant for gravity, the K constant for the spring, the relaxed length of 15 meters, which I used from behind the scenes video and iterating the model to match the real life YouTube video. I then initialized the variables used to calculate potential spring and spring force, and I calculated the initial amounts of energy in the entire system. Throughout this time interval, we used 6.5 seconds based on analyzing the YouTube video. I then defined the force of gravity, the spring force, and the net force in order to calculate the ball's velocity and the position. I then updated the spring and updated the energies in order to graph the change over time. Here's the video of the glow script program in action. You'll notice that here you can see the person dropping with the rope, and you're going to see them curve up like the rope swing we saw in the video. You can see that the delta E total over time is remaining at 0, which means that the energy principle is satisfied, which is what we're looking for. And as you see me scroll down, I'll show the X and Y position graphs, which I will explain in a little more detail after this. Here are those position graphs in greater detail, the X on the left and the Y on the right. And you'll see that the X position data returns to that initial value of about 15. We started negative 15 on the left of the rope, and then 15 on the right, since we moved from left to right like this. You'll see that in the Y position that we started at about 32 meters and ended at about 32 meters, which is correct. And you see that we remained off the ground by about 3 meters, which is what they were talking about in the video, 10 feet, which is about 3 meters. Here's the energy graph one more time, just to show that the total change in energy over time was 0 throughout our entire experiment, which means that the energy principle was satisfied. In reality, some energy would be lost to heat or drag, but this is an ideal system that did not account for that. The maximum spring force that we calculated was about 2140 newtons, which is about 460 pounds of force, and it took place at about 3.136 seconds, which is towards the bottom of this rope swing. The maximum velocity of over 36 miles per hour took place a little bit later because it takes some time to transfer the spring potential energy into that kinetic energy. To improve the comparison, one would include a drag force to improve the accuracy of the net forces acting upon the person during the rope swing. Another way to improve the model would be to obtain the accurate positional data from the YouTube video in order to allow for a more exact calculation of initial position, K constant, and forces acting upon the person. When describing the motion of the person, it is clear to see that there is a constant summation of gravity, spring, and drag forces acting to create a net force on the person, but it is difficult to name all these components and model them properly, which is why we did not include the drag force in our glow script model. We utilized Newton's second law to update the net force, velocity, and position of the person as they move down their rope swing, with the application of predicting motion of swinging objects given some initial information. We also utilized the energy principle to show how kinetic energy, potential gravitational energy, and potential spring energy can be transferred between each other during a rope swing. We utilized these energy equations in our glow script code to model the changes in energy over time, and shows that the total change in energy was equal to 0 during the entire experiment, which meant that the energy principle was satisfied. Overall, we created this computer program in GlowScript to model the motion and changes in energy, and we calculated the maximum velocity and spring force, which we found to be large numbers that were very unexpected for a traditional rope swing. Thank you very much for watching.